Okay, Assalamualaikum and good morning. For this third part of this chapter 1, basically we will go on the noise analysis. Okay, noise is mentioned here because it will affect the experience, okay, of the receiver part in any of the communication system. So some noise can be filtered out, okay. So there are general way to minimize noise is either to use the component that contribute less noise and to lower their temperature. So the measure of noise usually will be expressed in terms of the SNR, signal to noise ratio, where we have this is the signal power divided by the noise power. Okay, so it can also be stated in terms of the decibel value or in terms of the absolute value. So usually a very high SNR is preferred lah, okay, to have a best performance. Okay, so noise can be divided into two category: correlated and uncorrelated. So under this uncorrelated noise, basically it will be further divided into two, which is external and internal noise. Okay. So the correlation basically implies between the relationship between the signal and also the noise. So correlated noise will exist only when the signal is exist. Okay. So uncorrelated noise, on the other hand, it will present all the time, whether there is a signal or not. Okay, so this one will depends on signal. Okay, if we have a signal, then only we have a noise. Okay, but here it will present all the time, whether there is signal or not. So the external noise, okay, generated outside the device or circuit. Generated outside the device or circuit. So there are three primary sources, okay, for the external noise. Either man-made or you have atmospheric, and the other one is extraterrestrial. Okay, atmospheric noise naturally will occur when we have the electrical disturbance, okay, that originate within the Earth's atmosphere. Okay, so commonly called the static electricity. So the source of this static electricity naturally when we have the lightning. Okay, so the frequencies above 30 megahertz. Also, the atmospheric noise is relatively insignificant. For the extraterrestrial noise, also consists of electrical signal that originate from outside Earth atmosphere and is therefore sometimes called the deep space noise. So this one originate from the Milky Way, the other galaxies, and also the Sun. So extraterrestrial noise can be further divided into two categories, the solar and the cosmic. Okay, the man-made noise are simply noise that is produced by the mankind. Okay, the predominant sources are basically based on the spark producing mechanism such as the electric motors, automobile ignition system, power generation equipment, and others lah. Okay, so somehow it can be densely populated in the industrial area and is therefore sometimes called the industrial noise. The internal noise, basically the electrical interference which is generated within a device or a circuit. So there are three primary kind of internally generated noise. Short noise, the transit, time, and also the thermal. Okay, so we can go through all of these. Basically, can be further elaborated. So the short noise are sometimes called the transistor noise. So it is additive with the thermal noise. So the short noise is basically in the electronic devices lah, such as the diode, transistor, and so on. Okay, so for the transit time noise, basically it will occur when you have a modification, okay, to a stream of a carrier as they pass from the input to the output of the device. So such as from the emitter to the collector of the transistor, so that it will produce irregular or a random variation which will be categorized as the transit time noise. Okay. Okay, for the thermal noise, this one is actually associated with the rapid and random movement of electron within a conductor, okay, due to the thermal agitation. So when we have this random movement, it will also produce an AC component. So the thermal noise are present in all electronic components and also the communication system. So because thermal noise is uniformly distributed across the entire electromagnetic frequency spectrum, so it is often referred referred to as the white noise. Okay, so the analogy is basically analogous to the color white containing all the colors or the frequencies of light. So thermal noise is a form of additive. Okay, so this is also called the white noise. So it is additive noise, so means that it cannot be eliminated. Okay, and then it will increase in intensity with the number of devices in a circuit with the circuit length. So therefore the thermal noise will set the upper bound on the performance of a communication system. So the AC component usually will produce from the thermal agitation have several names lah, including the thermal noise, white noise, or the Johnson noise, based on the name of the founder of this noise. So it is a temperature dependent. Okay, so the Johnson noise lah, after the name the man who relate the Brownian particle movement of the electron movement. Okay, so the thermal noise is the random motion of the free electron within a conductor caused by the thermal agitation. So Johnson proved that thermal noise power, okay, so is Johnson, okay, the man that named after this noise. So he proved that the noise power is proportional to the product of the bandwidth and also the temperature. So mathematically we can write like this. Okay, where we have the Boltzmann constant here, which is this K value, the Boltzmann proportionality constant, okay, in terms of joule per Kelvin, 1.38 10 power of minus 23. Okay, so this T is temperature in Kelvin, this is the bandwidth. Okay, so this is the noise power. Okay, so to convert the temperature from Celsius to Kelvin, you need to add to 70. So the temperature, it should be so we will have in terms of the Kelvin value, okay, whatever temperature here. So the Boltzmann constant here, sometimes in the I think in the calculator you have this constant value. Okay, so this is, for example, if you have 100 Celsius, so the temperature would be 373 K. If a 0 Celsius, temperature is 273 K. So you can also express in a logarithmic function, okay, in the dBm value. 10 log KTB divided by. Okay, so that will be in terms of the dBm. This one, the noise power in watt. Okay, so the room temperature is stated in the absolute value. Okay, if they call it as absolute value, the room temperature is about 70 degree. So the absolute value of this T will be 290 K. Okay, when it comes to the room temperature, the absolute value. Okay. So the notation for this, sometimes we can write it's just either N or PN. Okay, it's the same for the noise power. So the thermal noise is basically random and continuous, occur at all frequency. So it is predictable and additive. Okay, so present in all device. So this is why the thermal noise is the most significant, okay, of all the noise sources. Then we will move to the noise voltage, where we'll have somehow equivalent circuit for the thermal noise source, okay, where the internal resistance is in series with the RMS noise voltage. So for the worst case condition and the maximum transfer of the noise power, okay, so the load resistance is made equal to the internal resistance of the source. So when we have the noise voltage drop across the resistance, it will be equal to half the noise source. So this is the circuit. This is the noise source. Okay, so the noise voltage across this R is basically half of the noise source. Okay, so we know that the noise power developed across this load resistor is equals to KTB. Okay, so the mathematical expression, okay, for the noise voltage can be derived as this. So So we arrange that. Okay, so we will have the noise voltage squared is equals to 4R Okay, so this is how we develop the noise power across the load resistor. So the mathematical operation, okay, the noise source with equivalent circuit based on this. So the noise voltage is given by this. So for example, for an electronic device, okay, operating at a temperature, so example, the temperature given 17 degree with a bandwidth of 10 kilohertz. So determine the thermal noise power in watt and dBm, and also the RMS noise voltage for 100 ohm internal resistance. And 100 ohm of load resistance, okay, RL. So how to solve that? Okay, for part the thermal noise power. Okay, so we know that the T is given should be in Kelvin, 17 plus 270. So it's equals to 290 K. So we have the formula and the power KTB. Boltzmann constant 1.38 times 10 power of minus 23, 290 K, the bandwidth 10 kilohertz, 4.17, okay, watt. So to find the noise power in dBm, the value 4 times 10 power of minus 17 minus 134 dBm. Okay, so the RMS noise voltage which is using that VN formula of OR KTB. Okay, so that's the example of how you use and calculate the thermal noise power and also the noise voltage.